Okay, so hello everyone. I will just share my screen and get everything ready till people join. So, welcome to this course on electromagnetic theory, and this is a part of PMRF TA that I'm trying to do. So, I'm a research scholar here in IISc Bangalore. And in the last few classes, we had been talking about, we started with our very well known electrostatics, and then we gradually talked about, the different Maxwell's equations, how to derive those equations. Okay, so if you have a charge distribution, how to find the field for them, if you have a current distribution, how to find magnetic fields there. And then we talked about induction, that is how electric and magnetic fields are related to each other. From there, the very concept of electromagnetism as a single subject came up. And then we moved to electromagnetic waves. We studied about how waves propagate, what happens when a wave moves from one medium to another. So that was about the last few classes. And this is the eighth class. And today will be, uh, you know, transmission lines. Now, why this is interesting is because so one of the major applications of electromagnetic theory is about signal transmission or how waves propagate along a transmission line, or you can say basically circuits, right? So, but typically when we talk about circuits, we don't talk about what can we say? I mean, we don't talk about if you have a wire, suppose connecting different elements in a circuit, we don't talk about what happens in the wire as the signal propagates, right? We consider that it's a resistance-less thing, so it doesn't affect the signal. We just take into account the resistors that are there, the inductors that are there, and so on, right? But in many cases, and that's what we'll be reading today about when it's the case, but there can be situations where this connecting leads or the wires that are there that play a very important role in determining what signal actually gets propagated. Okay, so there can be attenuation of wave, there can be distortion of wave. So all these things can come up, and then if we know how these transmission lines are affecting our signal, we can tweak them in a way that they become distortionless, the power transfer becomes maximum. So all these things can be done if we have the knowledge about how this connecting leads or transmission lines are affecting our signals. So in today's class, what we'll try to do is we'll try to see that if you have a circuit, okay, and under what conditions the effects of the transmission lines actually become significant and where you can ignore them. So we will talk about the different regimes. And then when we are in the regime where the transmission lines are important, what are the different ways or different parameters that govern the effect of these transmission lines? And how do you use these parameters to characterize your transmission lines and then use that knowledge for better transmission, right? Okay, I don't know why this is not changing. One second. Something wrong here. Don't know if my computer got hacked or something. It's very weird. Hmm. Okay, so let's get going. Now, talking about lumped and distributed circuits, right? So let us consider the situation where you have some, element. Consider this to be some combination of circuit elements, okay, where this is your input side, excuse me, and this is your output side. So you have some I1 at the input and you get the output at I2 after it passes through this lumped element, right? So what you can see here is that, so if this is your initial signal at the input end, when it comes out of this lumped element, you get the same signal. What this is telling you is that when you have a lumped element, this is the nomenclature that we are using, that if you have a lumped element or if you consider a circuit where the the transmission through the circuit does not affect your signal, right? So whatever you have at the start, you get the same thing out at the end, okay? Then it is called a lumped circuit. Okay. So basically what I mean is in a typical circuit, if you had something like, some source, okay, just ignore those things. So you have some source and then, suppose some resistor and another resistor or something, right? Now, if we look at just this part of your circuit, suppose there are wires, right? Now, what you consider typically is that whatever current and whatever voltage is here, right, at this end, the same thing is here, right? Normally, we just consider the voltage drop across the resistor, across other elements. So this part of your circuit, right, where the input and the output do not get changed. So you can consider this as a lumped circuit element. Okay. But now what you can have is consider a case where you have a lumped circuit element, but then on the two sides you have some connection leads. Okay. Where what happens is at the start you have some signal, okay, and then it passes through this connection lead, then the lumped element. So that means whatever signal is here, the same signal is here. That's the definition of lumped element, right? And then it passes through another connection lead and reaches your output. But as you can see, these two signals are not the same, right? So there is a lag that comes in this term here, right? So this lag is coming because of some connection leads, which is causing the delay. And it depends on, so basically, this is taking care of the fact that your signal will take some finite time to travel, right? So there will be some delay that will come in. And that delay is basically causing your this delay in the signal between the input and the output, right? And that is coming because of the fact that you have a connection lead of certain length and the signal is taking certain time to go from one end to another. So there can be phases that can come in. Now this connection leads can also distort your signal. It can also lead to attenuation of your signal, right? So now while the lumped part of the circuit, like where this part, okay, so today we are actually talking about transmission lines, and we are talking about the regions. We'll talk about different regimes and how the transmission lines or the connecting leads can cause changes as the voltage or as the signal transmission happens. Okay. And we are trying to look into that. So now, uh, what this is telling you is that while the, so if you consider this lumped element, there is no change as the transmission happens through this, but the connection leads cause some changes. So now if you take the entire section, right, entire this region from the start to the end, considering including the connection leads, then you have to call this circuit as a distributed circuit. Okay. So while lumped circuit, we can ignore the effect of uh, the wires and the transmission lines. In a distributed circuit, the effects come in. Okay. So now we'll try to look at when can we call a circuit as a lumped circuit and under what conditions it becomes a distributed circuit. Okay. So that depends on the signal that is getting transmitted. What signal are we talking about? So that determines whether we are in the lumped circuit regime or in the distributed circuit regime, right? So let us look at these different regimes. So what it is telling you is that in the lumped circuit regime, I'll just change to Okay. So in the lumped circuit regime, this is the situation where the dimensions of your components, okay, so that means the wires or the coaxial cables or all that. So the dimensions are much, much smaller than the wavelength of the signal. Okay. If the dimensions are much, much smaller than the wavelength of the signal, then you can actually ignore the changes that come in because of the transmission, right? And so basically here we are considering that the voltages are not changing over connecting wires. And that typically actually comes from, like, it is derived from the concept of electrostatics, which says that, you know, what is a wire? Like connecting wires, there are some conductors, right? And we know that the surface of the conductors are equipotential surfaces. So there's no work done as charges move over the surface of the conductor, right? So using that, you can say that there's no actual potential difference or changes in the potential as the signal gets transmitted over the connecting wires. Okay, but this is a regime where you can ignore the effect of these wires, and that's the situation where the dimensions of the components are much smaller than the wavelength of light. And because they are much smaller, you can actually ignore the wave nature. Okay. And in this situation, in this regime, you can apply our typical well-known Kasharp's law that we initially, when in long back in our high school, we had read about Kasharp's law, and then like the voltage law and the current law, right? Which are very useful when we talk about circuits, typical circuits. So all these laws are applicable when we talk about the lumped circuit regime. Now, there can also be another regime, which is the ray optics regime, where it's the other extreme, where the dimensions are much, much larger than the wavelength of the light. Okay. So even in this case, what happens? The wave becomes rays. Okay. And even here, because the dimensions are much, much larger, you can actually ignore the wave nature. Okay. And this is a typical ray optics regime. Now, for our class today, what we are concentrating on is the transmission line regime or the distributed circuit regime. So this is the case when the dimensions of your circuit elements or the connecting leads or the wires, they are comparable to the wavelength of the signal. Okay? So when can that happen? So if you consider cases where your signals are in the gigahertz range, then the typical wavelengths that we are actually talking about comes in, you know, tens of centimeters, right? So now if you have a wire which is in this typical range, uh, like matches with this typical length scale, then we are talking about situations where the dimensions of your components are comparable to the wavelength of the signal. And now you cannot actually ignore the wave nature, right? And this is the region where the effect of this connecting wires become very significant. Okay. And this become like in regular days, this becomes very useful when we talk about microwave circuits, when we talk about optical fibers and so on. Now for a sinusoidal signature, wave, suppose you have some signal at some which is a 50 hertz, not 50 hertz, like consider some signal, very high frequency, maybe sinusoidal wave. Okay, sinusoidal signature. So then you actually know what frequency you are talking about, right? And you can actually find the wavelength from there and then use this idea that, whether your dimensions are comparable to that wavelength or not, right? But now if you have a digital signal, okay, some signal where you have something like this kind of a square wave. So what happens there? Now, if we look at the textbook definition, a square wave should look like this, right? But um, in like practical world, you do have a finite rise and a fall time. Okay, so like practically, this is how your digital signal will look like. So if we just take into consideration this part, the basically a switching condition where things go from some value to some value in some time, right? So there's some saturated ramp kind of signal. So if this is your signal in the like with respect to time, that is in the temporal space. Now what you can do is basically you can do a power spectral density of your signal, right? Which would actually give you the distribution of power as a function of different frequencies. Basically, you'd know what are the dominant frequencies in your signal. Okay, so suppose if you have some distribution like this, so you can say that the maximum signal lies within this value, right? So that gives you a rough idea of the region, the maximum frequency till which your major power is concentrated, power of your signal, right? So if you define such a frequency as the F max, then from there you can actually define a lambda short, that is the shortest wavelength. Okay, based on like if it is in free space, you consider like speed of light and like you can actually find the wavelength. Basically, once you know the frequency, you can find the wavelength, right? And this is how you will do it for a some digital signal. Now, what this means is that now in distributed regime, the physical length of the wires or the connecting leads, if they're comparable to this lambda short value, then we are in the distributed regime where you have to consider the effect of the transmission lines. Otherwise, not, right? Now, how do you define this comparable thing, right? What is comparable, or like how do you quantify that, right? So typically what you consider is if like zero point 0.1 times of the wavelength. Okay, so what it means is if you have some F max, maybe 30 gigahertz in air, and then the lambda short is, suppose for your signal, maybe that your lambda short, that is the shortest wavelength associated with your signal, comes. Then if your L, okay, if your L is more than 0.1 centimeter, comparable or more than 0.1 centimeter, then you are falling in the distributed circuit regime. Your wires or components have to be sufficiently smaller than 0.1 centimeter. It has to be smaller than 0.1 centimeter. If it is smaller, then you can ignore the effect and you can say that we are in the lumped circuit regime. But if it is equal to zero point 0.1 centimeter or larger, then it becomes the distributed regime, right? So basically 0.1 times of lambda short. That's how you can basically define your cutoffs, right? These are not very clear cut boundary between different regimes, but that's how you can roughly estimate. Okay. Now, so that means when we are in the distributed regime, we will actually have to consider the effect of your transmission line, right? Now, the effect of the transmission lines are defined in terms of few parameters, which we call the distributed parameters. Why do we call distributed parameters? Because these are defined as, the parameters are defined as per unit length, and they can vary as you go along as along the transmission line. They can change as a function of position in the transmission line, and and they are defined as per unit length. Okay, so that means these parameters are distributed across your transmitted lines, and that's why they're called distributed parameters. Okay, so how do you define the effect of a transmitted line, right? So you basically write the effect in terms of these four parameters: R, L, C, and G. Okay, so what you first do is see if you have a very long transmission line, what you can do, you can break your transmission line into smaller regions. Okay, how small? Such that each individual segments can be considered as a lumped circuit element. That means what? That if you have a long transmission line, you break it into sections of, suppose, like this delta Z, right? Sections of delta Z, where delta Z, this is like each length of delta Z is called the unit cell, and this delta Z is much, much smaller than lambda short. So that means this has to be determined based on the kind of signal that is getting transmitted, right? So if you know the signal that is getting transmitted, you can calculate the lambda short, and then from there you can try to define the length of your unit cell. Now in this unit cell, you can consider, you can use your typical, Kirchhoff's law and all of that. So you can, because just this individual unit cells are in the lumped circuit regime, right? So what is being done is that now you can consider this each sections as small circuits where lumped circuit regime holds. That means, if you just look at this section, what I mean is when the signal is transmitting over the entire length, there'll be some effect, right? How are we calculating that effect? So we are breaking it into small sections. Now, suppose if you just look at this section, which is your, unit cell, here, when your signal moves from this point to this point, we will consider that there is no change, right? Similarly, when the signal transmits from this point to this point, or, when it transmits from this point to this point, we'll consider that the signal remains the same, right? So in this parts, okay, we are not considering the effect of the wires, right? What we are basically doing is that we are considering that for this section, for this delta Z section, it's a lumped circuit. So what all matters is this parameters that we have defined for that unit cell, right? But if you look at the bigger picture, many such unit cells actually characterize your entire transmission line. So you are defining the property or the effect of the transmission line in terms of this, parameters. Okay. Now, why are the parameters distributed like this? Okay. So what this means is, now if you look at each section of your transmission line, each section of the transmission line has some resistance. Your transmission line cannot have, it's a conductor, we understand, but it cannot have infinite, like zero resistance, right? It cannot be. It has to be some finite value. So that's just the imperfectness of your conductor. So your conductor does have some finite resistance, and if you can find the resistance per unit length, that would give you the R in your, where is my curve? So that will give you the R, right? So it's associated with the imperfectness of your conductor, right? And then comes L. Why L? Because there's some current flowing through the wire, and we know that when currents flow through a wire, it creates magnetic fields, and then there are inductions that can happen. So that the associated field causes a net inductance in the wire, okay, for the wire. So L is modeling the magnetic field associated with the current that is flowing in your circuit or through the transmission line, right? So in each unit cell, you have a R resistance for your transmission line. You have a L inductance for your transmission line. Okay. Now, how do you know that the resistance is in series? You can also have parallel components, right? So any resistance in parallel is nothing but, you can define it as a, conductance, right? Now, why is this term coming in? Okay, so this resistance between, like, what is this physically implying? So it is talking about the imperfectness of the dielectric that typically lies between the positive and the negative terminals of a wire. So if you consider some cable, like suppose some coaxial cable or something, so we know that there is a positive like terminal, then you have some dielectric, and then you have another sheet of metal which acts as your negative terminal, right? So what this dielectric that is there in between, okay, what if there are imperfectness in it, right, which can result in some net, conductance. So that's the G, that's the origin of the conductance for your unit cell. Okay. And now, because you have two wires, basically in you have a plus, like if you, when you're talking about this, you will have a plus and a minus, and then the current will be flowing, right? So so this region, so you have two such wires. So two wires with currents, basically that means there are charges there, so that two wires can make a capacitor out of it, right? So it's the capacitor per unit length that comes in as C here. Okay. So C indicates the, so G talks about imperfectness of the dielectric, and C indicates the region between the two wires that make up the capacitor. Okay. So basically what this is telling you is that now if this is your entire transmission line, you break it into small sections. How small depends on what is the wavelength or frequency of the signal that we are talking about. Now, in each section, right, you can apply the lumped circuit element concept and consider that each of these sections comprise of an L, an R, a C, and a G in this format. Okay, L and R in series, and then you have G and C in parallel. So this in this way. Okay, excuse me. Sorry. So basically, in this way, for each such section unit cell, you have this, and then based on the length of your transmission lines, you can have many such unit cells joined one after the other. Okay, infinite number of such unit cells. Okay. Okay. So now what we'll try to do is, because the sections, individual unit cells, there, so each of the sections are lumped circuits, right? Like if we just look at this section, it's a lumped circuit. Overall, it's a transmission line distributed circuit, but each of this section is a lumped circuit element. So there we can apply the Kirchhoff's law. And if we apply the Kirchhoff's law, we can look at how things vary, how the potential is, how the current is as it flows through this circuit, right? Only this part, only the one unit cell at a time. Okay. So that's what we'll try to do now. Okay. Before that, one can derive the Kirchhoff's law from Maxwell's equations itself. So now that we know what are the Maxwell's equations, we can actually try to derive the Kirchhoff's law. Okay, and it would be quite interesting if you think of that. We know long back in our high school days, we have studied about Kirchhoff's law, but now it also comes back to us from the Maxwell's equation, right? So if you consider the Maxwell's equation with no time dependence, okay, so that means del B, del T, del E, del T, all these terms go to zero, okay, and then consider that there are no free charge like no rho, no J, okay, or basically no, you can actually consider some charge distribution there. It can be there, right? There can be some current associated, like in a circuit. So obviously there has to be. So you can just consider no time, no explicit time dependence, basically. So consider del B del T to be zero and del E del T to go to zero, right? So if you just do that, you would get this you would just get this four equations, right? Curl of E, it's actually equal to minus del B del T, but now because del B del T is zero, so it goes to zero. And divergence of E equal to rho by epsilon naught. Curl of H is equal to J, and divergence of H equal to zero. And now because del rho del T is also zero, you can actually consider that your J is divergenceless. Now, what is this telling you? Del rho del T going to zero, divergence of J going to zero. That's nothing but the fact that there is no charge accumulation. And that's our very well known current law, right? Which says that from a node, whatever current comes in and whatever current goes out, they're balanced, right? That is what I like identically implies that there is no charge accumulation at any point. Okay. So that directly comes from this fact that divergence of is zero. Okay. Now, if you again start with this curl of E going to zero, what it means is closed integral of E dot dl. That is nothing but the voltage. Okay. So over the entire loop, that is zero. So this is again nothing but your voltage law. What does the voltage law tell? The voltage law tells that if you have a closed loop, then the algebraic sum of the voltage drops should come down to zero, right? And that is what you also get here. Stop intercom. So that is what you also get here, right? Over a closed line integral, that means when you do it over a loop, the effective potential drop should algebraically go to zero, sum to zero, right? That's the Kirchhoff's voltage law. So basically, they're coming back to us from the Maxwell's equations, okay? So now for each such unit cell, we'll try to apply the Kirchhoff's laws and see what that tells us about the voltage and the current changes as it propagates through the unit cell. Okay. Okay. So now to each unit cell, if you apply your KVL, okay. So basically this was your unit cell, right? So you consider that here the input current is I, okay? And this is some voltage here at some Z. And as it transmits, the output is at Z plus delta Z. Okay, so that is your output voltage. And then in between you have this resistor, this inductor, and this conductance and capacitance in parallel, right? So what you can do, you can consider a loop which goes like this, right? The bigger loop, you can consider that. So what that tells you is, now look at the potential drops. So VZT, that's what you start with. Then there is a minus IR delta Z that comes from this. Okay, R delta Z is the resistance, and then you have I into R, that's your potential drop, right? So across the resistor. Then you have L delta Z into di dt, which is the drop across the inductor, right? So you're talking about the bigger loop. So you can just ignore this. So basically, you start with this voltage, you go, and then you go here. So that means there's no voltage drop here because there are no elements. So then you have V of Z plus delta Z, right? So this is how you're looking at the loop. Okay, so minus minus, that's why the minus signs, right? And that's how the loop closes, and that's equal to zero. This is your Kirchhoff's voltage law, right? So now with rearrangements, you can rewrite, and then considering that your delta Z goes to zero, like it's the limit, you can actually write it in terms of the differential forms, okay, derivatives, and this is what you get, right? Similarly, for this unit cell at n, you can look at the Kirchhoff's current law, which means the algebraic sum of the current, that is the amount of current coming in and the amount of current going out, should add up to zero. So that means if current I is coming in here, okay, and there will be some current going through the conductance channel, some through the capacitive channel, and some will pass on to here, right? So you start with IZT, then there is some current going out at G delta Z, okay, into V, and then there is another current, amount of current that is going through this path, which is given as C delta Z into del V del T, okay, and the rest goes out through this path, that is minus I Z plus delta Z T, okay. And then again, if you just take the limit of delta Z tending to zero, you can get this differential equation. So these are the two differential equations that come out of the Kirchhoff's laws for the unit cell. Okay. So now let us look at a simplified case where you can consider R and G to go to zero. So if R and G goes to zero, what happens? So these terms go away, right? These terms go away, these terms go away. And then if you can look at these two equations together, okay, you can get a second order partial derivative differential equation, and this is how it looks like. So if you look closely at this is nothing but the wave equation, right? This is how a typical wave equation used to look when we talked about EM waves. We remembered this is how it looked like, right? So this is the wave equation where this term here gives you the velocity of the wave. So that means the solution to this. Okay, so here you have voltages and currents, and then you can write the current in terms of voltage and get a second order differential equation in terms of for voltage. So that means the solution to this equation is the voltage, right, as a function of time and position along the transmission line. And that solution voltage is a wave. Okay, and it can be written as a summation of forward and backward moving waves, where the velocity of the wave is given by this relation here. So it depends on the L and C of your, uh, the different distributed parameters. Okay, now once you know V, you can actually find I, right? And basically, they should have a similar form where the ratio should give us the characteristic impedance. So now what is this characteristic impedance? Basically, it means that there's some impedance that your transmission line is providing to the signal. You have some incident voltage, but the voltage sees some impedance, some effective impedance as it passes through the transmission line. And that depends on how these distributed parameters are, right? And that is what is the characteristic impedance of your transmission line. Okay. And that is given by just as V equal to IR or IZ, right? So similarly, here it is impedance because it can have, there are capacitance and inductance involved. So it can have some reactive load. So that's how you can write it as Z is equal to V plus by I minus, V plus by I plus, right? The ratio of voltage to uh, current. Okay. Now, in terms of line parameters, what you can do. So now if you can, if you look at the expressions, the for this case where R and G are 0, you can basically write it as root over L by C, right? Okay. Now you have to understand here I minus is not the return current. It's not that the current going here and like not the return current. It's basically in along a line, along a transmission line, what is the reflected current? Okay. And B and the other way to A along the same path. Okay. It's the same path of the transmission line. Okay. Okay. So now there can also be cases where R and G are not 0. Okay. So there can be all such combinations of R and G. But these are the main two relations that has to be validated, or this is always true. But now based on different media, you can have different kinds of cases. Okay. Now in a general situation, what you can consider is therefore, because you have understood that the solution to the wave equation is some wave, right? So and that wave, so you can write the voltage in terms of something like V naught cos omega t minus kz, something like that, where z is along which your transmission line is. Okay. So in a phasor form, you can write it as real part of something like this, and then you can actually, for the phasor, what you can do is ignore the dependence, and you can just look into and write V as a function of Z as V naught e to the power minus j kz. Okay. So now if this is your form of your potential difference or voltage, okay, and if you apply this, like use this form, if this is your form, okay, now you use this for these two equations. Like here, when you have V and I, again I and V, like here, apply them, right? So what you get del V del Z as a function of time is equal to minus I as a function of time into R minus L di dt. Now here, when you do d I dt, you know that you have this j omega t kind of term, right? So when you do a time derivative, you get a omega j omega out of it, right? So basically, you get this equation, right? So similarly, for the other, like the KCL formula, like here, you can again do the same, and you get this relation, right? So now, if you know use both these equations together, what do you get? You get that del square V del Z square is equal to this term here into VZ, right? So again, if you look back, this is a very simple, second order differential equation, which has a solution like this, right? So del square V del Z square equal to minus gamma square VZ, where gamma is this term here, okay, will give you a solution of this form. So this is your forward moving wave, and this is your backward moving wave, right? So here, this term gamma is basically your propagation term. Okay. So it talks about what happens to the voltage as it gets propagated. Okay. And you can see all this R, L, G, C involved here. Right. So, and you can understand this is a complex quantity. So you can write it as something like alpha plus J beta, where this real part talks about attenuation. Okay. Attenuation or loss in your wave, while the beta part talks about phase. Okay. So there can be all such conditions where your alpha is 0, but beta is non-zero. Okay. Or your beta is 0, alpha is non-zero, right? So Alpha talks about attenuation in the signal, beta talks about phase differences in the signal. Okay, and that all of it comes from this propagator, this propagation term. Right. So now, if this is your, general form of potential as a function of position, okay, if you just consider the forward wave now, okay, that is V naught plus e to the power minus gamma z. Okay, and this is from this equation you can write it as something like this. So now what is del v del z? Del v del z is nothing but minus gamma into v naught plus e to the power minus gamma z, right? So now you can get a relation between you know iz and vz, right? This term this term is nothing but your vz, right? This is nothing but vz. So now basically you can write a relation between the two, iz and vz. Now, what will be the ratio of the two? That is your impedance, right? So, for some particular Z, what is Z? Be careful. So, if you have your transmission line, uh, th- 1 second. So, if you have your transmission line, here we are talking about this direction as your Z, okay? So, that means at any particular Z to some value, the ratio of voltage to current, okay? That's your impedance. And from here, you can see this is your ratio, right? So this is the characteristic impedance of your uh, transmission line. Okay. Now what you can do is, as you can see, this is a complex quantity again. So that means this also tells us that the voltage and the current are not in phase in general. Okay. There can be some certain conditions where where suppose these terms cancel out and become a real quantity. But in general, these are complex quantities. So voltage and currents are not in phase. Okay. Now here, if you put the expression of gamma here, you would get this form. So this is how you define the characteristic impedance of your transmission line. Okay. So now let us look at the different conditions that can actually arise based on the different values of R, G, L, and C. Okay. So again, in the lossless case, R is equal to 0, G equal to 0. Okay. That means this terms are 0. So we just get it as root over L by C. And this is same as what we had derived previously, right? So that is resistance that the voltage sees as it transmits through the transmission line. Okay. Now there can be also situations where your omega L is much greater than R. That's the case where your operating frequency is very large. Okay. So at very large operating frequency, what happens? Omega L is much greater than R, and omega C is much greater than G. So you can basically ignore these terms, right? And you get back the same form. So that means this is important. So high frequency case is similar to the lossless case, right? High frequency case is similar to the lossless case. Okay. Now there can be another situation where there is a ratio between the ratio remains constant. So L by R, which is basically the series time constant, right? If you go back, this is how it looked like, right? So L by R is a measure of the series time constant, where G by C gives us a measure of the parallel time constant, right? So if L by R is equal to C by G, then what happens is there is no distortion in the line. Okay, there can be attenuation. Okay, so there is a finite alpha which talks about attenuation. Okay, but the beta term is not there. Okay, so this is how it not really the fact that the beta term is not there, but basically the form of your signal remains the same. Okay, so you can, in this case, you can again write alpha as R into root over C by L. Basically, you are just, rewriting the term. Okay. And because L by R is equal to C by G, you can also rewrite it like this. Okay. And the Z naught again turns out to be root over L by C. Right. Now, if you talk about, what is the phase velocity, or what is the velocity of propagation of your, what is the phase velocity of this voltage wave, right? So if you consider the lossless case where alpha is 0, right? So basically, if alpha is 0, that means if you just look at this part here, if alpha goes to 0, your gamma only becomes j into beta, right? So if you just look at the wave takes up a form of v naught plus e to the power minus j beta z, something like that, right? So then you can actually write it as some term like this, where the phase velocity is now given as omega by beta. And what is beta? As you can see here, if alpha is 0, the beta has this form, omega root over L by C. And so this is the ratio. Now, if you remember, this is the same thing that we had initially got when we solved for the wave equation, right? So again here, when we had solved for the wave equation, we had seen that the speed of the velocity of the wave was given as 1 by root over LC. And the same thing again comes back here. Okay. Now there can be cases where you have a finite alpha. Okay. What that means is, so you had e to the power minus. So when you look at e to the power minus gamma z form, right? So there the j beta part will cause will give you the phase, while the e to the power minus alpha z will talk about an exponentially decaying signal, right? So that's a attenuation that is happening. Okay. And you can actually quantify it. So you can write it in terms of dB. Okay. So if you know the potential at certain z equal to 0, and you know the potential at certain other point z, you can take the ratio of the two, write it in terms of the logarithms, and then that will give you what is the attenuation in dB. Okay. So normally in questions, if you are said that, the potential at z equal to z naught is this much, the potential at z equal to, z1 is this much, what is the, you know, what is alpha? Okay. So in that case, if you just use this formula, right? If you just use this relation, basically take a ratio and then the logarithm, 20 log ratio, this will give you in the, so you'll first get it in terms of, like, whenever you're doing this log term, right? 20 log 10, you're basically getting the loss in dB. Okay. Now, if you want to just find the loss in, natural units, then you can just take the ratio. Okay. So there can be a conversion between the two, right? So when you multiply minus 20 log ratio, that gives you the value in dB per meter. Okay. While, so this is dB per meter, and this is the conversion factor. And this alpha here is in natural terms, right? So when you just take the ratio, you get the natural terms, and then you can actually multiply by this factor to get your, loss in dB. So these are just conversions which can come handy in solving questions. That's why, or, when you define a transmission line, you can define it in terms of dB per meter, right? So you in natural units how it is. So there you have to do these conversions. That's why it's important to that. Okay. But basically what it is telling you is when you have a non-zero alpha, there is an attenuation where the voltage, exponentially drops as it propagates through the transmission line. Okay, so now based on all that we have discussed so far, we can try to solve some questions, right? So here it says that a TEM mode transmission line is having distributed circuit parameters as given. So you have R, L, G, and C given. Now it's asked the line is what kind of line, right? So now you know what to do about it. It's a very standard question. So you know that if it is lossless, then R and G should have been 0, which is not the case. So this right away tells us that the first marker gone. This right away tells us that this is not correct, right? It has to be lossy. Now for distortionless, you have to apply the condition that we had just discussed, right? So for distortionless, we know that L by R should be equal to C by G. So in this kind of questions, be careful about the units, okay? Where you have nanohenry, where you have microsiemens, all of that, okay? Here you have picofarad. So be careful about the units. So for lossless line, R and G is 0. So that means it's not a lossless line because you have non-zero values of R and G. And then the distortionless line means that these conditions need to be satisfied. So if you take the ratio of the two, you see that they match. So that tells us that this is a distortionless line. Okay, and this is also true, right? Okay. These are very, very straightforward. Just looking into, like, just to recap the different relations and what are the associated, uh, type of transmission lines. Okay. Okay. Now, there's another question which says that you have a lossy transmission line. That means the alpha is not zero, right? And the resistance per unit length is given, which is 0.05 ohm per meter. And the line is distortionless. That means the R by L equal to C by G, right? Am I saying it correct? R by L equal to G by C. That has to be satisfied and has a characteristic impedance of 50 ohm. So that means Z naught of your transmission line is given. Okay. It is asked that find the attenuation constant. So basically, so you have to find alpha, right? How do you find alpha? So what are known? First is R is known, okay, and this is Z naught. Okay, so Z naught is known, it is distortionless, that is known, and it is lossy. Okay, so now what one can do is basically we have to understand what are the known relations that we have. If we go back, we know that, if it is lossless, if it is distortionless, then this criteria holds, right? So here, the alpha had this form, if you remember, right? So alpha can be written as R into root over C by L. It can also be written as G into root over L by C. Now from here, if you define alpha square, okay, where what do? You multiply this with the second one. What happens? The terms within the square roots cancel each other, right? So what you are left with is what you are left with is basically alpha square is equal to R into G, right? Just multiply this term here, R into root over C by L, with G into root over L by C, right? That's nothing but alpha square. So this gives you a relation between alpha square, alpha, and R and G. Now, in your question, R is given. You want to find alpha. That means you have to find G, right? Now, what can be done? What are the other questions? What is the other thing that is known to us? The other thing is Z naught is known, right? Z naught in the question is known. Z naught is nothing but L root over L by C, right? And root over L by C is nothing but, you can also write it in terms of R and, just use this relation, right? So what I mean is something like this. So for the distortionless line, R by G equal to L by C. Characteristic impedance is nothing but root over L by C. So root over L by C is nothing but root over R by G. Now R is known, Z naught is known. So you know G. Once you know G, you know that alpha is root over of R into G. Now you again know R and you also know G. So that means you can find alpha, right? So that's how you can actually use the different relations that we have been deriving, right? So if you understand, we had looked at this, right? We knew these two relations, but from here we got a new relation which relates alpha with just R and G. So that's how you have to use these relations, okay? So that's why this was a question that I tried to give. So now that's how you can find your alpha. Okay, so that's given. So R is known, Z naught is known. So that means you can find G. Once you got G, you can use this relation to find alpha. Okay. Now, if it was asked to find in, the decibel unit, then you have to go use this relation. Then multiply by this term, 8.686 term, to get alpha in dBm, dB per meter. Okay. So based on the question, you can use different relations. Okay. Now talking about terminated line. So till now we were talking about a transmission line, and we had distributed the transmission line into small unit cells, and for each unit cells we had this four distributed parameters like R, L, Z, and G and C. Okay, and we saw that based on the different values and what are the relations between the two, there can be different types of transmission line. It can be lossy, lossless, distortionless, all of that, right? But now in a closed circuit, okay, so there can be a load at one end, so your transmission line can be terminated by a load or something, right? It can either be, it can also be short circuited, but in a general terms, you would have some load at the, so if there's some source at one end, so if there's a source at one end of your transmission line, there'll be a load at the other end, right? Generally that's the situation. So you have a source, you have certain things, and then there's a load where you want to measure your maybe voltage or get the voltage out or something, right? So the question is, what happens in this case? If it is a transmission line of certain length L, we know that as the signal transmits from the source to the load, there is a change in voltage now, right? Which would come because of the transmission lines. Okay. So to understand that, and we know that as it propagates, it has this wave-like form, V naught e to the power minus gamma Z, both forward and backward wave, right? We know that form. So now the question is that how do we find the voltage or the current at different instances on the transmission line, while we take into account the fact that it is terminated at some certain Z with some known load impedance. Why? Because you can understand that when you have a load here at one end, your voltages and whatever changes in the voltage that is happening while it is transmitting, it has to it has to match certain boundary condition at the load and the source, right? That is important, because it just cannot be a random wave moving at some random, with some random gamma something, right? There are certain conditions that need to be satisfied at the two ends, the source end and the load end. So suppose in the load end, you know what is your load impedance, right? So that would govern the kind of drop that would be happening at the load site, right? So that's why it necessary to now consider the effect of the load. Okay. So that is what is being done here. So what you consider is you take the load at Z equal to 0. So this is a convention. You just consider that your load is at Z equal to 0. Okay. And as you go towards the source, you go to the negative direction. So basically your source, if your transmission line is of length L, then your source is at Z equal to minus L. Okay. Now, what it is telling you is, so V naught plus and I naught plus are not equal to VL and IL, right? So there has to be some, relation between what is the voltage and the current at the source side and the load side. Okay. So what we do is now we just look at the general form of voltage and current. This is the general form. We just derived from the wave equation, like by solving the partial differential equations, right? So this is your form of voltage and current. Now, what is the boundary condition at load? So at load, we know that the ratio of the voltage to current should be equal to ZL, which is the load impedance, right? Now, what is V at Z equal to 0? So if you put Z equal to 0 here, e to the power 0, and again e to the power 0, so it's nothing but V naught plus V naught minus, right? What is the current at Z equal to 0? Again, put Z equal to 0 here and Z equal to 0 here. So you get uh, into Z naught is also there, right? So Z naught gets cancelled. So basically you get this form as so when you are writing I naught, just put Z equal to 0. So you get V naught plus by Z naught minus V naught minus by Z naught, right? So that's this form that you have here. So that means at load, This is the relation that needs to be satisfied. So this relation actually is very important, because now you can see that the characteristic impedance of your transmission line is related to the load impedance using this relation. Okay. And this term here, this is just taking things common. This term here is the ratio of the incident to the reflected wave amplitude. That is nothing but the reflection coefficient, right? So the reflection coefficient again can be by using, ratio and proportions. You can get a relation that relates the load impedance with the characteristic impedance, and this ratio here tells us what is the reflection coefficient. So physically what it means is that your transmission line has some impedance, and then you have an impedance at the end. Now, how different these two are would govern how much of the voltage would get reflected back. If they are same, so if ZL is equal to Z naught, what will happen? There'll be no reflection, right? Okay, so now a similar boundary condition can also come up at the source. Okay, so now we will do the same thing. Okay, so we will try to find the impedance at the source, okay, at incidence basically. So what happens here? And we know that Z is, just by our convention, we know that Z is equal to minus L, right? So now we want to find the ratio of the potential at minus L and the like voltage at minus L and the current at minus L, right? So again, you use this general form, and now you put Z equal to minus L, okay, and take things common, and this is what you get. So what do you see here? That the impedance at the source, okay, at the source end, again depends on the characteristic impedance of your transmission line, the reflection coefficient, that means indirectly it's related to the load impedance that you have, and it is also dependent, obviously dependent on the, the distributed parameters which come in gamma, and then it depends on the length of your transmission wire, okay, how long, because that has this e to the power term here, right? So if you rewrite this, you can write it in this form, which gives us a relation between how the different parameters of your transmission lines can be used to relate the characteristic impedance of the line, the length of the line, or the load impedance with the impedance at the source. Okay. So this tells us that the load impedance that is given as ZL, right? The load impedance and the length of the transmission line. Okay. And also Z naught is there. Okay. So the load impedance and the length of transmission line is seen to now affect the impedance that is seen at the source. Okay. So effective impedance that happens at the source is a function of what is the load impedance, what is the length of the transmission line, how different is the, the characteristic impedance of the transmission line from the load, because that would govern the reflection coefficient, right? So all of this govern the impedance at the source end. Okay. So now there can be all these different cases that can come in depending on, what are the values of R, L, G, and C, what is the length of your transmission line, okay, and how different the different impedances are. So based on that, all different conditions can come up, okay. So for the lossless case, what happens? Alpha is 0. So you can replace gamma by J beta. So this is nothing but what you are trying to do here. Now, in this condition, when it is a lossless case, now what you can do, you can have different cases. If ZL is equal to Z naught, that is the impedance of the at the load matches with the characteristic impedance of your transmission line. What happens there? So if you put ZL equal to Z naught, then Zin is equal to Z naught. That means the impedance seen at the source also matches with the characteristic impedance for the lossless case. Okay. Now again, if you have ZL equal to 0, if your ZL goes to 0, that is more like the short circuit case, right? So if it is a short circuit, what happens? Your Zin is given by this relation here. You can also have open circuit where ZL goes to infinity, and then this is the form of your impedance at the source end. Now, in this form, you can now also have conditions based on the length of your transmission line. Okay, so if beta L goes to 0, then you can see Zin is equal to ZL. Okay, so if the length is too small, but then if you have beta L equal to pi by 2, so this, as you can see, depends on the wavelength that is getting transmitted, right? So here 2 pi basically is the phase that we are talking about. So 2 pi is basically associated with the wavelength of your 2 pi is nothing associated with the wavelength of your signal, right? So pi by 2 means that when the length of your transmission line is equal to 1/4 of the wavelength. Okay. So in that condition, Z in becomes equal to Z naught square by ZL. And this is a very well used, like very popular and extensively used form. Okay. So this is how you can see. So now the characteristic impedance and the load impedance governs the impedance at the source. Again, you can have condition where beta L is equal to pi. That means now length of your, so this means length is equal to, here length is equal to, array, one second. So here length is equal to lambda, this is lambda, okay, lambda by 2. So here length is equal to lambda by 2, lambda by 2. Here length is equal to lambda by 4. For this case, it's lambda by 4. For this case, it's lambda by 2. And here you can again see Zin becomes equal to ZL. Okay, so based on the length of your transmission line, all these different conditions can come up. Out of that, this is very widely used one. Okay, this one is very widely used. All of them are, but this is also very popular. Okay. Now let us try to solve some questions based on this, all that we discussed so far. Okay, so here it says that the input impedance of a short-circuited lossless transmission line, quarter wavelength. See, quarter wavelength means this condition, right? Quarter wavelength means the length of your transmission line is 1/4 of your wavelength. That is this condition here. Okay. Now here it says that the input impedance, that is Z in. Okay. We have to find Z in. And it says that for a lossless transmission line, lossless means R and G is 0. Short circuited means, so this is the condition, right? And there it's a short circuit. That means ZL is 0. So if ZL goes to 0, what does this tell us? What the Z in should be? It should go to infinity, right? So the input impedance of a short circuited lossless transmission line of quarter wavelength is what? It is infinity, right? So basically this Z in is equal to Z naught square by ZL. ZL is 0 because it's short circuit. And then Z in is equal to therefore infinity. Okay. So all this kind of questions that directly uses the formulas that we had been discussing about are pretty common. Now this is an interesting question where uh, you have multiple transmission lines, one after the other. Okay. And it is said that you have to find the characteristic impedance of this part of your wave. Okay. You have to find Z01, considering that no reflected wave is present beyond A. Okay. So, how do we do it? Right. So, here to start with, you have to understand because it's like a nested kind of thing, right? So, one after the other, layered. So, the output of one will be the input of the other. Like you can understand that it happens one after the other, right? Now, let us look at what are the different, informations already provided to us. Okay. So it is said if we just start with this part of your circuit, okay, only this part. Now here ZL, that is the load, is given, this 150 ohm, okay. and the characteristic impedance is given, and the wavelength, the length is specified. Okay, lambda by 4. So that means we can actually find Z in, right? What is the input impedance at this terminal, right? So you can find Z in, you can find Z in for this part of your signal, of your transmission line, right? And what will that be? Z naught square by ZL, right? Basically, you're using this formula. Z naught square by ZL, you know Z naught, you know ZL. So you have to find Z in. Very simple, right? So if you do that, how much do you get? So 30 into 30 by 150. Okay? So that is 6. So that is your Z in. But things have to be continuous all throughout this, different sections of your total transmission line, right? So now it says that Z in here is 6. Now this input impedance of this section is basically nothing but the load for this part of your transmission line, right? It's the load for this section. Now, what do you know for this section? You have to find the characteristic impedance. You know the length. You know the load, right? So what it means is, again, if we go back for this part, we know the load. We have to find this. So this is something we want to find, the Z naught. So that means we need Z in. So we need the input impedance for this part of the wave, right? We need the input impedance for this part of your transmission line. Clear? So if we use this, so if you use a different color, what we saw from here, we knew the characteristic impedance, the length, and the load, and we saw that this is basically 6. This is the impedance at this end, which is 6. Now this is the load. So for this section, so now if we change the color and maybe go to blue. So for this section, what do we know? We know that your ZL is 6, right? That's the only information we have. We want to find what? We want to find Z01. That is the characteristic impedance. So this is not known. So what do we need? We basically need Z in, because all of them are quarter wave transmission line, right? These are all lambda by 4 length. So that means if we know Z in, we can use the Z in the question. So for this, what we'll use? So it says that there is no reflected wave beyond A. So that means at this point, okay, whatever, so here the characteristic impedance of, okay, so now I'll change the color again, okay. So for this point, right, so for this part of your wire, you know that the characteristic impedance is 100. If there is no reflection at this point, that means the impedance is must match, right? Only then. So if the impedances match, only then there'll be no deflection, right? If the impedance at this point is different from what you have at this point, then obviously there'll be a reflection. So because there is no reflection, that means the impedance at this end has to be 100 ohm. So that tells us now that this is 100 ohm. Clear? So now what happens? Sorry, what did I write? Not that. Uh, Sorry, there is a mistake. The mistake is that it's not Z1. That's we have to find, right? So So basically, this turns out to be 100 ohm. So now you know the load, you know the input impedance, you have to find Z. That's quite simple, right? This formula, you know the load, you know the input impedance, you have to find this. So this is 100, this is 6, 100 into 6 into 4, right? So that will give you the characteristic impedance of this section. Clear? So if we just look at the solution now, Z in at 2, like at this point, it's Z naught 2 whole square by ZL. Okay, that gives you 6, which is at this point. So for the first section, ZL, so here if you look at ZL is 6, okay, Z naught we have to find, and Z in is 100. Why? Because there is no reflection. So this is 100. So this is 100 and this is 6. This is lambda by 4. So then again we use this relation. So 6 into 100 and square root gives you the value of the characteristic impedance at this part of your transmission line. Okay, so that's how you can try to solve this types of questions, right? Okay, so there are similar questions I've seen in the last year's assignments. So similar questions can also come up this year. So that's how you have to solve this kind of questions. Okay. Now this is another similar kind of question. Okay, where it says that you have a transmission line, right? So you have a transmission line with a impedance, characteristic impedance given as Z naught. You know the source, the voltage at the source, okay, and you know that there is some impedance here, which is also given, right? The characteristic impedance is given, and you know the load, which is also there. You have to find Z in, right? So now, see, for this part of your section, like, just if you just look at this part, right? So here, whatever is the load here should be the load here, right? So that means if you just look at, this section, you know ZL, you know Z naught, and it is the length is known, is lambda by 4. You have to find Zn. So that's the same formula again, right? Z naught square by ZL should give you Zn. Okay, so what is Z naught square? 50 into 50, right? So if you have to solve it, this is like 50 into 50, right? Divided by what? ZL. ZL is 25. So this should give you the value of the input impedance. Clear? This is very straightforward based on all that we have been discussing so far. Once you know Z in, now the question is find the voltage, what is the voltage at the input side? Okay, so what is the V in? So here there are two things. So now when you're trying to look at the voltage, you're trying to look at both the amplitude as well as the phase, right? And you know the amplitude and the phase at the source. Okay. Now what all do you have between the source and between this point? So there is some impedance here, and there is some impedance that is coming because of the transmission line, right? Some transmission line. Now we know that impedance. So the impedance at this end is nothing but Z in. So that is coming out from this part of your question, right? So now that you know Z in, Okay, so 50 into 50 by 25, that is 100, right? So that means Z in is 100. Now if Z and ZG is also 100, that means whatever voltage you have here, it is like you have some and like some voltage, okay, and that gets distributed between two resistors like this. Okay, so R1 and R2. Now this voltage gets divided between these two resistors R1 and R2. Now based on the ratio and of the two, you know how to divide the voltage, right? So that will tell you how the potential, like the amplitude will get divided. 10 volt, and this is some R and this is also R. So we know that the voltage will equally get distributed, right? So that already tells us that if your starting amplitude is 10, now it should be 5. Clear? Now that's your amplitude. Now how will the phase be? Now you can see, whatever change in phase happens, that happens in this section, right? When there is a transmission along the transmission line. But in this part, there is no phase change, right? What I mean is then whatever phase is here, the same phase should come in here, right? So if you write this as 10 e to the power j30, the same, j30 phase should also come in the V in. So now you know the amplitude, how to find the amplitude. So to find the amplitude, you have to use the typical idea of voltage division, how voltage gets, divided between different resistors in a circuit. That's all. And how the slope, how the, the phase part is coming. That is because here it should be in the same phase as the source. So if you know you know, the phase at the source, you know what is the phase here, right? So that gives you V in. But now when you look at VL, it's important. So at VL, as the, you know, as there will be a propagation along the transmission line, there will be additional phases that will come in. So the phase at VL will not be equal to the phase that you had at the source. Okay. It can it can come out to be equal, but because after some time it can just gain the same phase based on the length, like in a typical case. But it'll be like, after a total 2 pi phase, it can again come to the same. That can happen, but basically you'll have some phase added to your wave because it is transmitting along the transmission line, right? How much? We'll try to find it. Okay. So now for this part of the question, that is to find VL. How do we do it? So we know V in. Okay. So V in has this form. We want to find VL. So if we look at the typical form of VZ, right? This is the typical form of VZ for any Z, V at any particular Z is given by this relation here. For lossless transmission, as given in the question, your alpha should be 0. So alpha is 0. So gamma is only J beta, right? Gamma is only J beta. So if you put it here, we want to find, we know what we have at Z equal to minus L. We need to find what we have at Z equal to 0. So let us first in our general formula, substitute for the case of Z equal to minus L. So Z equal to minus L is the source point, right? So if you put Z equal to minus L, then here you have J B beta L minus J beta L, all of the term. So here important to note this TL term. This TL is your reflection coefficient. Okay. That is coming from the fact that your ZL, the load, and Z naught, that is the characteristic impedance, are not equal. Okay. So there is a finite reflection that will happen because of this inequality. Okay. And that comes in this term. TE, TL, that is the transmission, what I'm saying, the reflection coefficient. Okay. Okay. So now you have this V naught. So you can write the V naught plus in This is like the amplitude of the forward moving wave in terms of this relation. So here what do you know what is the voltage at minus L, that is nothing but V in, right, which is already known to us. So that is 5EJ30. And then you know this terms here. So for solving this, if you want to find V naught plus, you want to find what is TL. Okay. And you want to put in the value of beta L. Now you know L is lambda by 4. So that means it's a pi by 2 line. Okay. So beta L can be substituted equal to pi by 2. So now this is known, this is already known, this is known. You just have to find TL. TL is the reflection coefficient. So that is given by this relation here. So you know ZL, you know Z naught, how different they are from each other. So you know the the reflection coefficient. Okay. So basically now you know all of it. So if you know the form of your, this is the amplitude. And now if you put in, you want to find VL, which is nothing but V at Z equal to 0. So in the general form, this was your general form, right? So in the general form, put Z equal to 0. What do you get? You get V naught plus into e to the power 0 plus TL into e to the power 0. E to the power 0 is 1. So that means you end up getting V naught plus 1 plus TL. So the value of the deflection coefficient will come from this relation, and this will come like the V naught plus can be evaluated from here. So now you know what is the load, voltage at the load. Okay. And the fact that you have this term here, right? So these are complex quantities, as you can see. And the fact that you have this term here tells us that there'll be additional phases that will come in. Okay. So the phase will not be same as what you had at the incidence. Okay. So here you had e to the power J30. This will have some different phase, and the amplitude, which will come from this relations. All these relations you have to use. Okay. So that's how this can be solved. So these are some typical questions from last year. So you can, work this out, and then similar questions can also come up this year. So that's how it can be helpful. Now, because, when there's this impedance mismatch, we know that, there'll be waves that, or voltages that will get reflected, right? So now you have a forward moving wave and a backward moving wave. And we know from, normal uh, understanding that when you have this forward moving and the backward moving and they come together under certain conditions, you can have standing waves, right? Now, for lossless case, considering alpha to be 0, you can write the typical expression of potential, voltage by this relation. Okay. And there, this part is your reflected wave, right? So you can write it nothing but, like, you can write it in terms of the forward moving wave by multiplying it with this term, where this term is your reflection coefficient. And in general, your reflection coefficient will be a complex quantity. So it will have a phase term and a modulus. Okay. The modulus will govern how much is the amplitude of the wave, reflected wave, and phi, the phase, is how different of the two forward and the backward moving waves. Right. Now, there can be different conditions that can arise. So if you have ZL equal to n times Z naught, okay, then you can write an expression for the deflection coefficient, which will be nothing but this, right? So now if you have n equal to 1, where ZL is equal to Z naught, that's the case where impedance have matched, right? So there you can see that the reflection coefficient goes to 0. So basically, there is no reflection when the impedance matches. That makes sense, right? So whenever there'll be a impedance mismatch, then the wave sees a different kind of obstruction, right? So then that's the reason why waves get reflected back. If there's no difference in impedance, there's no reason for the wave to reflect back, right? You can also have case where it's a short circuit, like ZL equal to 0. So there, what happens? So that means whatever wave was propagating, if you put it in the form here, so you would get a -1. So what it means is that while there is, you know, the amplitude is 1, but there is a pi phase that gets added, right, to the reflected wave, right? So now what you can do is you can put it here, put the value of your reflection coefficient here, and rewrite the expression for the voltage. And this is how it looks like, right? So now if you want to write the complete form of your voltage as a function of both space and time, this is how it would look like. So you have a 2 V naught plus sine beta z into sine omega t, right? And that's a typical form of a standing wave. For a propagating wave, you have something like, omega t minus beta z, omega t plus beta z, all this kind of form, right? But here you have product of two um, sinusoids. One is talking about the temporal change, another is talking about the uh, spatial change, right? And that's a typical form of a standing wave. So that's when a standing wave can come in. Now another, so you can also have a case where your ZL tends to infinity. That's like a open circuit standing wave. Okay. So now for the case where your reflection coefficient has a modulus of 1, there you can imagine that when the maximum that you can have, the maximum amplitude of the standing wave could be the summation of the two waves, which is like 2 V naught, and the minimum would be 0. Okay, that's the ideal case where the reflection coefficient is 1. But there can be situations where the reflection coefficient is less than, okay, and that's more realistic. And there you can understand. So now the maximum voltage will be slightly lower than 2 V naught, and the minimum voltage will be slightly larger than 0, right? So it's the ratio of these two, the max voltage to the mean voltage, that okay. So this is the resultant voltage of the standing wave. Okay, the max to mean will give you the standing wave ratio. Okay, and that is actually a measure of the amount of reflected power that you are getting. Okay, so if you, for a question, if you know the reflection coefficient, you know the standing wave ratio and vice versa. Okay, so that's these are parameters that are actually used to characterize different transmission lines. So if you have a transmission line, or some suppose you're talking about some microwave circuit, right? So there it's important to know what is the reflected power, and there it can be defined in terms of this voltage standing wave ratio, or VSWR, right? Or the return loss. So that's just the difference between the incident and the reflected wave. Okay, now so from whatever we had been discussing so far, what we got to know is that for cases when we are in the distributed circuit regime, the there is a contribution of a very significant contribution of the connecting leads or the connecting wires, okay, or the transmission lines. And if you know the properties of the transmission line, suppose you know the distributed parameters, okay, and you also know what you have at the source, then what you need to do an impedance matching for maximum power transmission or for minimum reflected wave to come in. And so the load can be effectively chosen accordingly. So suppose now you know the load, suppose the initially the starting load is some ZL which is not equal to the source impedance, then you have to have a matching network, something you can add some loads in series, or you can add some loads in parallel if you want to decrease the impedance. So in a way, by adding new you know uh, impedances to the load end, you can match your network, okay, so that the impedance gets matched. And that's the condition where the maximum power transfer will happen. That's the case where your source will remain protected. So suppose if you have some generator at one end and it has some impedance, and while you know the circuit is not impedance matched, what can happen is there can be a significant amount of reflected power that can come back to the source and that can damage the source. Okay, so in those cases, especially when you're talking about microwave circuits and all that, you have to be careful about this impedance matching. Okay, and as you can understand that, so what governs the properties of the transmission lines are this four distributed parameters that we just discussed, right? R, L, G, and C. And they can change based on how your transmission line is. So if you have some, if you have some distorted, twisted coaxial cables, or you turn them, twist them, all this kind of bends, okay, or if you tie them in this kind of fashion. So all this results in poor signal handling, because that disturbs the impedance of your circuit, that can result in, that can disturb the impedance matching, and that can actually result in reflected powers and all that. So especially when you're talking about, dealing with antennas have a very specific, uh, so if you have an antenna at the load end, it would have a very specific impedance, or load impedance, as a function of frequency. So then you have to be careful at which frequencies you are working at, okay, so that the impedance remains matched in the range that you're working. So all these things are very important. So if you have these connectors of some, different impedances, and you mix two, then this would result in some backflow, some reflected power. So these are poor, signatures of poor signal handling that needs to be avoided, if you are especially talking about some sensitive, dealing with sensitive instruments, or talking about sensitive measurements. Okay. So yeah, so that's a general idea about transmission lines, and how one should be, when one should be careful about their effects, under what regimes, what conditions, and how one can characterize them. How does the effect come in? What are the different relations? Okay, so that's what we discussed in today's class. Um, if there are any particular doubts, I'll hold on for some more time. If if you have any doubt, we can discuss further. Okay. So in the coming class, we'll try to actually talk about situations like, so now we got the idea about what are the different factors that can be used to, characterize, or characterize your transmission line. But now if you want to have a impedance match circuit, so we talked about this matching network, right? So if you want to make a matching network, which can be very useful when you're talking about, microwave circuits, or all that. So there are different, ways of, graphically representing this impedances, and the phases that gets developed, and all of that, which makes this calculations much simpler. So in a very complicated circuit, where you have different, you know lengths of transmission lines, they're going over different distances, and different sources with different phases of, like, different RLC. videos later and get back to me, either in the Teams chat or ask me the next day. So you can do all of that if you see the videos later. So that is also possible. Okay. Just hang on for some time so that if anyone, you know, comes in or joins for some questions, then we can try to address them, right? This type of questions are very interesting actually. There are many, like especially very common in exams and like multiple choice kind of things. Like this kind of questions are very, these are quite standard, but interesting and like common. Common in the sense, like widely. Like I've seen quite a number of questions. These are also similar noise. Okay, so this was the standing wave part. I think that is it. But yeah, I just so these are very useful because now that we are working in our, like while I'm doing my work, so when we make circuits, so you can understand this may look very simple, but these are very important points. Okay, the length of the coaxial cable. Suppose if you have like in a circuit, if you have very large cables involved, that would actually, and you're doing very sensitive measurements where time delays are very critical, then that can mess up. So you have to reduce your length of cables such that those problems do not come in. Okay, so these are very important when you talk about microwave circuits and things like that. It might seem very trivial when you're talking about normal circuits at lower frequencies and all that, but for microwave circuits or optical fibers and all that, this becomes quite important factor, especially with antenna. That's also very important because for antenna, so there can be different types of loads. Some loads can have a impedance actually does not have a does not change much as you change frequencies, but there can be, and like for antennas they have a very selective kind of behavior, so there the impedance do change significantly when you change frequencies. So then you either need a matching network which counters for impedance match, very critical and particular about which frequency range you are working on. Otherwise, there can be significant backflow and that can actually damage the source that you're working with and all that. Okay. So those things are quite important, like from a very practical point of view. And this transmission line effects also come in the fact that, so when you have long distance transmissions, the fact that you have this finite R, L, G, and C, that can result in loss, as we saw, right? There's a non-zero alpha, that means there'll be attenuation. So that actually, disturbs transmission at longer distances. And so you have to have constant impedance matching and changing of the transmission lines accordingly and all that, or you have to use much higher, make up for that with higher voltages so that you get a transmission to much longer distance. So transmission at long large stretches is that's why not very trivial. Okay, so in many cases, if you could actually transmit DC signals, that would have been much easier because there this C or L effects would not have come in. Okay, but again, what do I say? Converting high voltages, high DC voltage to low DC voltage, and all these conversions, or because in day-to-day life we need AC, right? So then you also have to convert from DC to AC, and all this in certain cases also need very bulky infrastructure. So that's why the use of DC in transmissions are still not that popular than AC, where you can have actually transformers and you can step up, step down very easily. But then for AC, you have this criticality of impedance matching. There's an effect of skin effect where, which increases the effective impedance of the network that you're talking about, and this sensitivity towards inductive or capacitive effects. So those things are crucial when you're talking about transmission at longer distances or these kind of wavelengths. Okay. So yeah, I think that's it. So thank you. If there are any questions, feel free to reach out. Okay. Thank you.